is my presentation I put together on transformers and large language models for signal processors and applied mathematicians. Okay, and this is a prequel of my or preview of my uh, uh, what I'll be hopefully presenting this in the coming semester for the deep learning class. But I tried to emphasize here like intuition. So the problem I had is I'd been reading all about transformers and I just couldn't really get my head wrapped around it. Okay. So I really finally just took like a week, and I spent a lot of time. I really drilled in, and ChatGPT is really good for answering questions about it, but it's the papers themselves. Okay, I'm sorry to if I hurt anybody's feelings, but the papers are impossible to understand. Oh, there's the pizza. So everybody, hi Simon, thanks for helping out. So the papers are hard to understand. So I sort of defrabulate them as to the best of my ability. And I want to present this in a sort of intuitive way for a signal processor. So all the concepts of, so all the the key idea is to present the basic concepts of transformers and large language models to cover the concepts in a hierarchical manner. So rather than just like say, do this, do this, do this, do this, like sort of try to provide a little structure to how the motivation by what it's doing, emphasize modular abstract thinking. And okay, the most important thing is to draw the flow diagrams from left to right. I mean, I cannot understand a flow diagram that goes from bottom to top. I mean, come on. Okay. And the key topics are attention layers, transformers, um, encoding and decoding, generative pre-training, and inference. Okay. So this is sort of a high level view of what, okay, at least for the special case of language modeling, what a transformer does. So it has an encoder, you have some text, it gets broken up into tokens by an encoder, and then it goes into the transformer layer. And, the way to think about transformers, at least from my point of view, is that almost the same way you think about blocks in a convolutional neural network. Everybody get your pizza, okay? The blocks in a convolutional neural network that once you understand one block of a transformer, you can just string them along as many times as you want, just like a convolution block in a convolutional neural network. Okay. And then when you're all finished, you reproduce it like you replicate it like nx times. Nx might be, 15 or 80, and then you do the decoder. Okay. Oh, that should say decoder, not encoder. Now, in order to understand this, you have to start off with that core block, which is the transformer layer, and the most important component of that, or the key defining component of it, is what's called the single head attention layer. Okay, so once you understand this, you've got like 80% of it figured out. Okay, okay, so this one figure here has got a lot of information in it. So there's three things that go into it: Q, K, and V, which are query, key, and value. Okay, we'll later see why it is they're called this. Okay, but in my view, okay, the first thing that you've got to understand, that's very important to understand, is that the Q, the K, and the V are not parameters. They're not parameters of the model. They're the inputs to the model. Okay, to me, that's super confusing when you're reading about this, because it feels like they're supposed to be parameters. They're not. They're the input. Okay. Then each Q, K, and V, K and V have to have the same shape, but Q can have a different shape. However, both Q and all three have to have the same length. Why? Yes.
Professor, where does the Q, K, and V come from? Does it come from the encoder?
Hold that thought. Okay, so Simon's question was, where do they come from? Don't worry about that. They come from somewhere. Okay, they're input. So and in fact, they can be all kinds of things. Any kind of data you can put into those as input. Okay, so this is just the way to think about it is like, I like to think of it like a convolution block, that your input could be an image, it could be another output of some other block. You can just string these together. The important thing is that Q, K, and V are inputs. Okay, they're inputs. And that the output here doesn't have a name. I just call it O, okay? But and the output here always has the same shape as Q, the query. And that the key and the value both have the same shape, okay? And that the length of this matrices of the length of Q, K, and V are all the same. And we'll see why in a minute. They have to be the same. Okay. Okay.
Does the math?
Okay, that's a very good question. What does the length mean? So the way to think about, let's just talk about Q, okay? Because that's the most important one in a sense. What Q represents is a sequence of inputs in time, okay? Where time is going in the vertical direction. So this is, the first vector is the time 0 vector. This is the time 1, time 2, time 3. And you can have as long a sequence length as you want. I drew through here because 4 here because, you know, like I didn't feel like drawing like forever. But this could be as long as you want it to be. It doesn't matter. Okay? And Q can be as long as you want it to be. K and V have to be the same, but they can also be as long as you want them to be. Okay? And each row, you see how I drew this? Where I drew each row like this. It's a matrix, but the rows are special because each row is essentially a feature vector. So each row represents a single input at a single time. All the rows have to be the same length because all the feature vectors that go in have to be the same length. So it's like a convolutional neural network. When you have a convolution, it has an input size, right? And then it has an output size, right? Okay. So is everybody good with that? Okay. These W's are linear transforms, and the output of the W doesn't have to be the same length as the input to the W, but whatever the output lengths are, they have to all be the same. Here, let's just assume they're all the same. The matrices are square, okay? These matrices, the W's are the parameters of the model. Those are the parameters. Those are the things you train, okay? The K, the Q, and the V are inputs, okay? Okay, so now once you have that, okay, what happens is I'm going to go through this. I have some slides that break down each of these, but let me go at a high level. This first block here computes the cross correlation between the keys and the queries. Okay. So what happens is that for each input in time, it's checking to see which of the keys it's closest to. See, that's the key point that, no pun intended, that there are 3 keys here. So you're deciding which key is best for each input. Yeah.
But so is it really doing the multiplication between the weighted Q and the weighted K?
So the best way to think of the weights for now is just to pretend they're not there. Okay, because it doesn't, what it does is it's just a linear transform. You can assume that the W's are square, okay? And it just transforms the input vectors to new input vectors, okay? It's just some kind of linear transformation. One of the key points that's really important to understand is that this W operates on each input vector individually, not all together. Okay, so for each input vector, there's a linear transform to another linear vector, and that's really critical because that's what means that each input gets processed separately. That's why you can have as many inputs as you want. You can double the number of inputs. It's perfectly happy because it's operating on each input individually
With the same weight.
with the same weight matrices. The reason you put the weight matrices in here, these 3 weight matrices are the only thing you can train. The rest of it's hardwired. Okay? It's hardwired. Let me say that one more time. The rest of it's hardwired. So if you set these weight matrices to the identity or you just take them out, there's nothing to train here. Okay? Nothing to train. Okay? Yeah.
So it's like some weird version of bank of correlators then?
Yeah, it's not a weird, it's a bank of correlators.
Yeah.
It's doing is it's taking each query vector and correlating it against all the keys.
Yeah.
And we're going to see what it does is that the key it correlates best with, it sends that output value. Okay. I'm, what I just said was not true. Okay. Because I tried to simplify to make it easier. You'll see it's actually, it takes a linear combination. It takes a combination, but it basically takes the best match. Okay. All right. So, okay, so the parameters of the model are these W's, the output is the O. I think the next slide now focuses on this matrix multiply. So everybody in here is good at linear algebra. That's why I said this is transformers and large language models for signal processors and applied mathematicians, okay? So this is the part that's intuitive for you, that you take you multiply this Q matrix by K transpose. What it gives you the cross correlation between all the things. So you can see there's three keys, and there's the other thing that's really hard to understand about the papers you find is they always make the number of keys and the number of queries the same. So that the matrix is square and it's really confusing. Okay. It's easier to think about it when they're not the same, because that's then you can see that the matrix now is 4 by 3. Okay. So there's three queries, there's 4 inputs. If there had been 17 inputs, then this would be 17 by 3. Okay. And what happens then is that each entry here represents the correlation of that. So the one row of this thing represents the correlation with each one of the keys. Okay. So here you can see that the first query vector had the strongest correlation with the first key. Okay. So that's the one you're going to want to output. Okay. Now, if you've done anything with deep neural network, okay, networks, you know that what you do here is that if you want to find the largest of these, you don't take the max, you take the softmax. Okay. It's a standard operator. So you apply the softmax across each row of this matrix. Okay. It's critical that it's across the row. Okay. However, there's one little thing that they came up with, which is critically important, or it doesn't work. You have to divide by dk. What's dk? dk is the length of this vector right here. It's called the model order. Okay. So if the vector is of length, so dk, so I don't know. So maybe this is 512. These vectors are all 512. Okay. Then you divide by 512? Do you divide by 5? No, that's wrong. You divide by the square root of 512. Okay, there's an error. Okay, shoot. Okay, I'm gonna have to fix that, because that would be horrible if I had the wrong thing. Okay, I'm gonna do this. This is an example of square root. I'm not going to change all of these because it would take too long. Oh, I can't believe I did this. Okay, anyway, I'm not going to, okay, okay. Imagine that's a square root, okay? I'll fix it later. Someone remind me, Jing Song, are you here? Remind me.
Is there intuition about why it's DK as opposed to like the length of the other thing? So like you have.
Why is it the square root of DK? Yeah, here's my intuition.
DK, because I feel like the previous slide.
Yeah. I can't, oh, you know what? That's a PDF. I can't change it. Yeah, go on.
Go back on previous.
Yeah.
Yeah, this one. So, there, the CK is, which one is the DK?
DK is the length.
Oh, I see.
Yeah, the DK is the length of the output of the W's.
No, is that right? Because on the bottom you've got the
Yeah.
DK associated with K and Q.
The DK is there.
Right, yeah. Right, so that's part of K, Q and K.
Oh, there's also an error. How come that's, oh, that's right. That's right. Yes, that's right.
Right, so I think that makes sense because you're
Yeah.
dividing you're normalizing by the number of entries in the.
But you're normalized by the square
Right,
root.
yeah, by the square, sorry, yeah.
The reason why you pick the square root, here's my intuition. If you normalize by DK, that would sort of make more sense because it would seem like it's then that would actually be the correlation. But what it's doing is it's sort of saying, oh, but I want to weight it more heavily if the vector's longer because I have more confidence. It's sort of like a heuristic that they throw in there that is found to be work well, that as the model order goes up, you want to do a stronger softmax. That's my intuition. Okay. All right. But yeah, but that's a magical scaling that's important. Okay. And then you do softmax across the rows. Okay. Right. Okay. So you do, this is the softmax, right? Now what happens is now the rows sum to one after the softmax. Okay. Okay. Then what you do is, oh, yeah. Okay. Yeah. Oh, okay. Then what happened? Oh, yeah. Is this? Yeah. Oh, okay. So then the final thing you do is after you have the softmax is that you take now S and you multiply it by V. Okay. So what ends up happening is that whichever one of these three is largest, it picks off the corresponding entry of V for its output. So this is what James was saying, that the intuition here is it takes for each query input, it takes that by input, I mean a single row vector of the query matrix. For each query input, it searches through all the keys to find the one that's closest. Then it outputs the value of V corresponding to that key entry.
Professor.
Yes.
So the outputs are not the same length as the inputs, right?
No, the outputs are the same lengths as the
But
inputs.
V, when the WV has a different dimension, you go to the previous slide.
Oh, yes. Okay, I'm sorry. Yes, you're right. WV, I lied. The outputs are in different dimension at this point. Okay, but then they'll come back. You know, you could do things. I'm going by what is the most common convention. Okay, but yes, and the reason that these outputs are different dimension is because the next layer is going to be an MLP, and the MLPs are notoriously computationally expensive. So you want to try to reduce the length of that vector. Okay, but the intuition here is that okay, so everybody knows. Okay, so this is called a single head attention layer. Okay. Yes.
So when you multiply S and V, you described it as though it was picking the largest probability, but really it should be taking a mixture of them, shouldn't it?
It is totally picking a mixture. I lied on purpose for simplification. So if this was one and the other ones were zero, it would only pick that one. But it really takes a combination of them. Okay. And we're going to come back to that. That's very important.
In your example, the top 3x3 submatrix there had symmetry, but in general, it's not symmetric for this, right?
Yes, that's correct. It's in general not symmetric. It's not symmetric. Actually, I just threw some numbers in there and, I don't know. I was in a hurry.
Yeah.
Okay. I probably should have made it more general. All right. Any other questions? Okay. So now you put this all together and this entire block is called a single head attention. And its inputs are now here, okay, Salman, the input for V and K are usually seem to be the same length because that's DM. That's viewed as the model order. The output of this and this are assumed to be of the same length, and the output of that is assumed to maybe be different. Yeah. Okay. And okay, good. Now what happens is okay, you do the obvious thing that you always do in neural networks, you replicate it. So you now, instead of just having one of these, you have H of them. Okay. Just because, why not? Okay. But now whatever the Q, the K, and the V is, they're all the same for all of them. However, the weight matrices themselves are different. Okay. Oh, I kind of screwed this up because there's supposed to be an I. These are supposed to have eyes under them. Okay, that's Jing Song. Could you take notes on my corrections? Okay. Then what you do is now what happens, and this is why, by the way, Salman, your point was really good. That the outputs here are not the same length as the inputs here. Why? Because what you do in a multi-head attention is you concatenate these all together, so it becomes a lot longer, and then you have to put that into an MLP. Oh, the next thing is going to go into an MLP. So usually then you have another linear layer here that like concatenates everything. So that last linear layer, its input dimension is whatever the vector length is for one of these heads times the number of heads, h. Okay? Yeah.
So why stack layers like that as opposed to increasing, or I guess you call it model order, one of those D terms?
Okay, so if you increase the D terms, it's doing something very different. Increase, we'll see in a minute. The D terms, the best way to understand what the self-similarity, this multi-head the single-head attention does is to look at the self-attention. No, we'll see in a minute. In self-attention, what happens is, are you familiar with the non-local means algorithm? Okay. Well, it's just what it's doing is you have a long sequence of tokens. That token is finding the other tokens in it that are most similar, and it's averaging them. Okay. Okay. However, the other heads are kind of doing other things. Okay. So it's like having different heads is doing something different than just having a longer encoding. A longer encoding just gives you more specificity for each token. Gives you, okay, is intuitively what's happening. Okay. So now if you do the multi-head attention, so what happens is you have the inputs, they get multiplied by the W's, then you have all this stuff. I made the same mistake many times here because I left out the square root. And then you have the things that are gold here are the trainable parameters. Okay. The gold things are trainable. The white things are just fixed. Okay.
And the only nonlinearity is the softmax.
And the only nonlinearity is the softmax. It's pretty wild, isn't it? Okay.
Is there any nonlinearity in the multiplier set?
Well, there will be, but we haven't gotten to it yet. This is just the definition of the multi-head attention. Yes.
I think that last W you meant the 7 O is the superscript.
Oh, yeah. Where is it? What did I do
In
wrong?
the box.
In the gold box.
This thing should not be.
Showing the dimension, so
W super O.
Oh, W super. Okay.
you got Q, K, and B instead of their dimension.
I'm like super bad at this. Jing-san, could you write this down and ask for all so he can explain to you what I did wrong?
Super.
Yeah. I totally believe you, but I'm just really bad at.
So right here, he's got WO.
Oh,
This dimension.
Oh, that
He
should
just
be-
wrote this. This should be WO.
yeah, that should be WO, right? Oh, that should be WO, right? Yeah, that should. Yeah, thank you. All right. That's obvious, except for it's not obvious to me. So, okay, good. Now, okay, what happened? Okay, so now what happened? Okay, self-attention. In self-attention is a special case when you have all three of the inputs are the same. So now what happens is that your input Q searches all the other, so you give it a sequence of inputs. For each input, it searches for the input that's closest to it, other inputs that are close to it. Okay. Of course, it's close to itself, but it's going to also be close to other things. Yeah. Oh, yeah, this way. Okay, yes. So here, see, and this is why I kind of have some forgiveness in my heart for the people who did the original paper, because I think the reason why they draw from bottom to top is that the time is left to right in this flow diagram. But it's easier here. I'm drawing it so time is from top to bottom, but flow in the computation is left to right. So for each input, right, it searches for the other inputs that are similar, okay? And then it takes a linear average of those inputs that are similar and outputs it. So that's exactly what's called the non-local means algorithm in image processing. It's well known to be one of the best denoisers, but it's very computationally expensive, okay? So it's essentially the single head attention layer is essentially when you use self-attention means that the three inputs are all the same. It's essentially the non-local means algorithm. So, okay. Excuse me? It'll do that. Yeah, they make great denoisers, transformers, right? You can use them for all kinds of things. They're generic Lego blocks. That's why we're not quite to the point of the full transformer, but when you're all finished, it's a block that has the same shape input as it has output when you use self-attention, and you could just you can just chain them together.
It's doing some kind of denoising on cue.
It's essentially doing something like denoising.
Well, I'm trying to understand.
Or it can do that.
Does it
It can do many things.
That's where I'm going.
Yeah,
Yes,
it's better not to think about
Well,
that.
here's-
No,
here's an
it,
example is in tech. Doing programming, and you've got a typo in one variable name that doesn't match all the other variable names that should be. So you would get a high correlation between the true variable name and these ones that are slightly off.
yeah.
Okay.
And if all the other ones have the correct name and this one's wrong, then, well, you should flag it and correct it.
But obviously it pulls out, in the end, we get massive magic, right? Because ChatGPT is all based on this. Oh, one of my goals is that at the end of this, if you're to believe the papers that I've read, that you guys would be able to implement ChatGPT. It's not all that super complicated, okay? Okay, it's just the really hard part is the training, I think. So, and then of course, I'm sure they have a lot of special handling of cases. But okay, now, okay, so what is masked attention head? This is very important. Okay. Okay. First, what is masked attention? It's used to enforce causality when you're doing. So you don't need it for like image processing, but you need it for text processing. Okay, because you want to do. We're going to do auto-regressive models for people who've taken my class. Okay. And okay, and yes. So here's what happens. It's really crazy simple. In masked attention, all that happens is that you take the outer product, just okay, but you add minus infinities to the upper triangular entries of the matrix. Of course, I don't know exactly how they handle that in the computer. If they actually use a minus infinity token and everything works. But when you so then what ends up happening is when you take the log, when you take softmax, this becomes just 1. Or here on this row, what'll end up happening is this becomes like this will be not 1 but large, and then that one will be smaller or something like that.
So softmax on the non-negative infinity portions and then zeros.
Yeah, exactly. That's essentially what it does. But in the computer, apparently they actually put minus infinities because it's faster.
There's a flow representation technique.
Yeah, so I guess because the reason is when you go to parallelize it on a GPU, it's easier to handle that case. Conditionals are the worst possible thing you can do on a computer that's parallel, okay?
So it's like, he's asking the model not to answer somewhere that he sees something.
Well, what it's doing is this. It's saying so people who've taken my class, 641 for short, know that the upper triangular matrix is the anti-causal part, right? If you have things in time, that's everything that occurred after your current time. So what this is saying is only pay attention to things that occurred before you.
So like the future Q values would only depend on the past key values
It will only depend on the past key values.
or vice versa.
Right. Now the self-attention, this masking is only done, as far as I know, in self-attention, but you could in principle do it with other things, but 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 here for self-attention, it makes particular sense because you're only taking inputs that were previous in time. Okay. That's going to be really important. Okay, so then what is mass self-attention good for? It's good for, the idea is you want the outputs, you want each output to only be processing things that occurred before it. And we're going to see what we're going to do next. I mean, where this is all going in the end is you're going to run this entire thing just to predict one token. Okay, you're going to go through the whole thing because what you're going to train to do, you're going to train this thing to do is you're going to train it so that the output sequence is one step ahead. So you have a token sequence input, the token sequence output, but you shift the token sequence to the left one click. And then you're just at every point you're trying to predict the next thing. So you'll get this output in the lower right-hand corner is where all the action is. That's the thing you want that predicts the next word. Okay. Usually tokens correspond to words. Okay, but not always. Like if you have supercalifragilisticexpialidocious, it might break it down. Actually, you probably make that a single word too. But yeah. But if you have some really unusual, infrequently used word, then it might break it down into smaller pieces. Okay, or some crazy sequence of nonsense letters. Yeah.
So it was my understanding that, so you said at the beginning, you can have any length input and output, but it was my understanding that it was like actually, it was a fixed length input, and that's the concept of context. And then you have this thing called like a null token.
Okay, we're going to get to that, but the input can be variable length. However, a particular language model puts some limit on the maximum length because the transformer will run too slow. The computation is order n squared, where the n is the length of the sequence. So you don't want the sequences to get too big. So they put a maximum length on the thing, and well, I'll talk about that later. But the maximum is typically like something like 8,000 tokens. So it's crazy. Like, I mean, honestly, we don't have to worry about the world being taken over by ChatGPT because it's like it's got senioritis, right? It like forgets what it was talking about 8,000 words later. Okay, which makes it a little bit like me. But so, all right. So now, okay, now this is very important, I'm told. I'm told. Their normalization. In the original paper, there's two ways you could do. Oh, first of all, there's two different ways to do normalization. You can normalize by what's the difference? Oh, you can just normalize the variance. Oh, this equation's wrong. I have to fix it because there is no. Oh, no, it's not wrong. You could just normalize by the standard deviation, or you can normalize by the mean and the standard deviation. Okay. No, I think this is the more common of the two. But I think some people think that's better. Maybe Open AI uses this. I don't know. It's like one of these things. Like people have strong opinions. I don't know. But what's more important is this. If you've talked about, everybody here probably knows about block normalization, right? The batch normalization. Okay. The problem with batch normalization is that you have to, like, during training, you try to estimate the mean and variance of the things and then adjusting, you save it, but it's kludgy. What people do now, which is better, is they just compute the normalization, and then these are not trainable, these are not learned parameters. They're just intermediate calculations. Does that make sense? Do you understand what I'm saying? And each input vector has its own normalization. So each input vector of length 512 or whatever, this is the model order, has its own, is normalized to have 0 mean and standard deviation of 1. And those are just, and you just back propagate through that calculation. So this eliminates all that crazy stuff you have to deal with batch normalization that I always disliked. Okay. So that's what they do. Now, in the original paper, they put the normalization after the multi-head attention, but now the widely accepted view is that it's much better to do it before. So what that really means is that the K, Q, and V inputs are normalized so that they have mean and 0 and standard deviation of 1 for each vector that's coming in, okay? Then you do a skip connection because you always do skip connections. I don't know. It's just a thing that everybody does, okay? So the folklore is you do that because it avoids vanishing gradient, okay? Then what happens is you do an MLP, but you do normalization and a skip connection for the MLP also. By the way, if I didn't have these slides here, I would have forgotten all this. So, yeah, but it's not that horrible, right? I mean, you can write the code to do this. That whole thing altogether is a transformer layer, and its output is expected to always be the same shape as its input. So that is a single block. You can think of it like a convolution block. By the way, the other way to think of the MLP is as a 1-by-1 convolution layer. Okay, because the MLP is not getting applied to the entire thing. It's just getting applied to each output vector one at a time.
Okay.
That's an important thing to keep in mind. Otherwise, that MLP would be way too big. Does everybody understand that? Because that's a really important point.
It's like applying the MLP separately.
To
multiple times.
each one. So it's and I know that's true because I asked ChatGPT and Chat said, yes, you're exactly right. Okay. But this is great question. Yeah. Because this is the kind of thing that's very hard to extract from these papers. Okay. All right. Is everybody good on? Okay.
So does it not produce a single output vector and then you just concatenate it onto the known input? It actually like somehow pushes it.
Well, it produces all. So if there are 10 input vectors, then it will produce 10 output vectors. It produces the same number of output vectors as input vectors, whatever that is.
Okay.
You seem skeptical.
Where's the prediction? Is that against?
Oh, don't worry about any prediction. Okay. That's the whole beauty of this. Here, we just let go. We're all free. So here's the thing is, it's just like to think of it like a convolution block. It's just a thing that takes gobbledygook in and produces gobbledygook out. Okay. Right now, we haven't gotten to prediction yet. Okay. So,
We've got the same shape.
but the important thing is the gobbledygook has the same shape.
And that has to be true because of the skip connection, like that there's a direct connection.
Yeah. Oh, yeah. That's a really good point. Yeah. Okay.
Not the length, right?
Excuse me?
The length of the vector.
The length of the vectors is the same also.
So,
Yes, the output shape is the same as the input shape.
Professor, then for the skip connection to hold true for the first one,
Mhm.
so the output earlier we said it has a different shape than the input.
Oh, no, but it doesn't. Okay. Yeah, it gets a little confusing, but that is true.
That
Okay.
O has a different shape than Q.
But that O does. Right. Oh, so no, because this W, okay, I wrote this wrong. It has an input of H times DH, but has an output of DM, and DM is the same as the input of DM. See this
You are
this
talking self-attention kind
so this DM here is the vector is the length of the dimension of the input, right? Okay.
So the WQ produces something with the shape DK, and the WV produces something with H.
Well, maybe okay, maybe so
So I think that the convention is.
this is the self-attention.
Like normally, like in matrix multiplication, if it's m by n, and we get m outputs. But I think in this, the convention is backwards because they typically multiply on the other side.
No, I'm doing it the regular way.
Okay.
Okay, so I see what you're saying. Yeah, I'm multiplying on the left.
Right.
That's true.
So that's not the typical linear algebra.
Oh, that's true. Okay, I'm sorry. Yeah, I'm multiplying on the left. Okay, I'm assuming all the multiplications occur on the left. I guess I would have been better if I had done it on the maybe I should have. I did it. You're right. My convention was infected by what I read, This is how they wrote them. They assuming multiplication on the left. Yes, that's
I
correct.
mean, that's fine, you just have to like be.
You
clear.
have to be clear about that. Yeah. So the output of WO is D sub M, and that's the same as the size of the input, D sub M. Because we're doing self-attention here. Okay. I'm just assuming they're all the same anyway. Oh, they are all the same. Yeah. Well, V doesn't have to be the same, I guess. But yeah, I'll go and double check this. Yeah. But yeah. But in the end, this is definitely true. That it's when you're all finished, the output shape for one of these transformer layers with self-intention has to be the same as the input.
So if we go back 2 slides,
Hmm.
or maybe slides. That one there. So WQ, WK, and WB. We input tokens to them, and then they output into the embedded space, right?
Right.
But then out is O back in the token space, or is that in the embedded space?
O is in the token space. I believe that's true. Yeah. Because we have a skip connection that goes around the whole thing, so it has to be.
That's true. There's a difference in the.
Yeah.
Okay.
Charlie Harrell has a question.
Yeah.
I understand self-attention. Does anyone ever actually use different keys and values?
Yes.
That's for translation, right?
They use that in translation, but they also use it in okay, yeah. For the standard, they only use self-attention, I guess. But they use it in translation.
You can give the entire text, but it's to translate it, so you have, that's
Yeah.
also when you don't say it.
I'm trying to think, there's a few times when it comes up that people use it, but I can't remember exactly what they are.
So you're like translating, you can like look at the beginning of the sentence and the end of the sentence that you want to translate.
Sure,
go
but
to the next word.
are the keys and values supposed to correlate to lexical terms?
Yeah. So what happens is that with if you think about it, so from a kind of a high level point of view, what's happening is when you're trying to do translation, the keys and the values will be different than the cues because you're trying to translate from one language. You're trying to find a mapping between like concepts in one language or words in one language and the corresponding words in another. Which
There,
makes
there
sense.
are application use that you can use that for data compression.
Let me try to say it so that you can see. Oh, for data compression, that would be another good one. Yeah. But there are definitely cases where people use different ones. Okay. But the common case that's done in ChatGPT is the self-attention, I believe. And then so this just shows, okay, this is the transformer. And now the transformer, you can have NX replications of this. And these are all the models. And here I did subscript it by the eyes. I forgot to subscript it before by the eyes. Okay, because you have different weighting matrices for each layer of there's for each head and then each layer. Okay, so there's a lot of parameters because you have different parameters for each head and you have different parameters for each layer. Okay.
But so
Yeah.
is there an assumption that there has to exist correlation in the space you are looking at the input?
Uh-huh.
Because, for example, I can imagine you can have one row to be like text, and the other row can be image, right?
Oh, you could do something like that. I've never seen that, but
They
that,
do it in the later space, right? They map it to later space and they
Yeah.
look for correlation. So there should be some correlation in the space you're working. Otherwise, you cannot find that.
yeah. Well, yes. So in the attention is all you need paper. Well, the paper's almost impossible to understand, but when you read blogs about it, okay, they have this idea, but you have to be careful. I mean, there has to be designed so that the spaces can talk to each other. And the way I don't want to, way they do that is that they'll feed they'll feed the outputs of this of an encoder into the cues of the oh no, into the no, they feed it into the oh, that's one of the things that's super confusing about these papers. Okay, you have Q, K, and V. But when they draw the diagrams, they reverse it. Okay. And they put Q on the right. Okay. And they put the K and the V on the left. Okay. And they'll feed. So, yeah, you have to be very careful about that. I killed a lot of time trying to figure that one out. Okay. Anyway, let me continue. Okay. So, this is helpful, maybe. This I compiled. I mean, I wouldn't jump off any buildings based on this, but this is what I believe the parameters are in some popular models. So let's pick this one. This is the most one of the more recent versions of Llama. Okay. It's got 80 NX, that's the number of transformer layers, is 80. DM, that's the model order. It's the length of the vectors, is 8,192. H is the number of heads, is 64. Okay, now, if you know DM and you know H, then you know DH, okay? They have to be divisible by one another. So they have 128 of those, okay? Then the MLP order, so this is the dimension of the internal layer. So what ends up happening in the multi-level perceptron, there's how many hidden nodes you have in the MLP. So it has 28,672. And the context window is 8,192. That's the part where it only remembers the last 8,000 words. Yes.
What is the relationship between DH and DM? Is that just saying that WO has to be square?
What it is that let me see. So
I think it is like if you have DH that's like 1H time of DM, then when you concatenate H of this together, the last layer, that gives you DM.
yeah. So let me
H times DH is equal to DM.
let
That's
me
how we measure the output dimension to that.
let me show you. It's so what happens here is this thing here has to be the same shape as that thing, okay? So for that to be true, you have H of the multi-head attention layers. So that means when you whatever the output is of this thing, and that's the output of this thing is DH, that times H has to equal DM. In other words, so you have like 10 you have 10 multi-head attention layers. You have 10 single head attention layers concatenated together to a single multi-head. So when you take each of those outputs, you concatenate together, you'll get something 10 times larger, and that has to fit the original model order. So put it another way, DM has to be divisible by H.
I guess I don't understand why WO couldn't have a different shape there, because that is just saying that the dimension of WO has to be square.
Oh, what you're asking, why does this output here have to be the same shape as the input?
No.
Okay.
Why does the number of rows of O have the same number of columns?
Oh, it doesn't. The number of rows of WO, this thing got screwed up, so ignore that.
The last row.
Why does the last?
You're saying that this matrix has to be square.
No, not.
DH times H
Oh,
DM.
yeah, I guess that's true.
So that could have an arbitrary shape in principle.
It can't because
It should not be. Then we can't do the skip connection.
you're
Yeah, maybe that's more.
Pearl, I think you're making a good point, which is that maybe they don't have to have that constraint, but they do.
The Q has the dimension of n times DM. So the skip connection, to do the skip connection, the W should.
Oh, you know what? I may actually have an error here. You know what my error may be? I'm drawing this as part of the multi-head attention, but I bet that's not true. I bet you just found an error. Okay. I'll have to go back and redo these slides. Thanks. The reason is I bet what's true is that matrix is really part of the MLP. And I got it screwed up. I have to go back and check. I bet that that's true. Okay, I bet that's true because the skip connection is a constraint that means that they have to have the same dimension. Let me check that. Jing Song, could you write that down as another one of the things I have to check? Okay.
But on this slide, you list the NLP matrices as different from WFO.
Right. Yes, but I might be wrong. Okay. Yeah. Okay. Let me go check that. Okay. I'll send you the slides and you can check them. Okay. Because you're good at this. Okay. All right. Good. All right. So this thing has 65 billion parameters when you're all said and done. Okay. And then here are some papers that you can look at that have all the various junk in them. Okay, now GPT style LLM models. So this is just like how you did the transformer, but then how do you use it to do something? Okay. Okay. So now, okay. Okay. The first thing you have to understand is encoding, which is really not that bad. Okay. It's really not that bad. So I want to start off by don't panic. Okay. Okay. So you have a sequence of the characters that come in. Let's just say it's ASCII because it's easier. Okay. You have a sequence of ASCII characters, and I'm not handling the spaces correctly, so don't worry about that. Okay. You have a sequence of ASCII characters. Okay. And what it does is it has a vocabulary. All right. The vocabulary is typically large, like 50,000. The vocabulary is a long list of character sequences. Okay. Each character sequence is considered a token. So you have 50,000 character sequences. There'll typically be words. Okay. Then what happens is that, and you build that the details of how you build that vocabulary, there's some better ways and some worse ways. But generally speaking, what you do is you look for you glom together characters to create the highest probability sequences. You try to find high probability sequences. So then when the text comes in, you basically hash it against that vocabulary. You find the longest sequence that you can find in your dictionary. And then that each entry in this vocabulary or dictionary is mapped to a single symbol. So if it's 50,000, then you have the numbers 0 to 49,999. Okay. And then, so for each input sequence, you output a number. Okay. And by the way, if I had more time, maybe I could click here. It's sort of fun. Let me see if this works. Oh, yeah, here it worked. Okay, amazing. So here, okay. Okay, so it's nobody cares about this. Why? Because you can just get it. It's like a module that you just pull in, okay, import, and it just does it. So if you type in the dog is happy, the dog is happy. These are the tokens it gets broken into, you see, and these are the numbers it outputs. So there's 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, why 5? Because I had I hit return. So the character return was a symbol. Okay, so you see, it's nothing that complicated. Now what happens is that now you can take these tokens. It's reversible. Each token corresponds to a character sequence, so you can go the other way. So that's the only thing you need to know. Okay, demystified, right? So you take a character sequence and it first tokenizes it. Now there's 50,000 tokens. So when you do one hot encoding, each vector is 50,000 long. Okay. Of course, you don't really do that. You just do it conceptually. You could do it, but okay. Then you have a linear transform. That's important. That's this matrix. It's a matrix E. Okay. The matrix E transforms you from whatever the size of the vocabulary is to this m-dimensional space. This matrix is learnable. So that's a big matrix because it's 50,000 by DM. However, we'll save something because the decoder will use the same matrix. You learn them both together. They're constrained to be equal. Okay. Okay. Now, just to make things more complicated, you don't want to lose the transformer is agnostic to the position of each token. Okay. So you want to keep that information for speech processing. So you encode the position of the symbol of the token using positional encoding. I'm not going into positional encoding, but positional encoding is like something developed by people who didn't understand the Fourier transform because there's some kind of weird sine wave they stick in there, which is a function of position. And just believe me, and it's crazy. You just add it. You go, adding it's going to screw everything up. You go, yeah, but everything works fine with neural networks. You just do crazy stuff and it works fine. Okay. So that's what you do. Okay. So now if you have, so this produces 1, 2, 3, 4. So there's 4 outputs. Okay. Each of which is of length D sub M. That's the model order. Okay. Now, Now for the decoder, what you do is you take the transpose linear operator, and now you apply a softmax. Okay. You apply a softmax. And that generates a probability vector associated with each outcome. So now what comes out is a probability vector over 50,000 different possible tokens. Okay, is everybody okay with that? Okay. So now what you do is you take the sequence, okay? You put a sequence in, it gets encoded into these vectors. It goes through the crazy transformer thing, and you use the masked attention in this case. And then you decode it, and it produces a probability of a token on the output. Okay? Is everybody okay with that? Okay. Now, this is generative pre-training. Now you're going to know what generative pre-training is. It's nothing all that special, honestly. Okay, it's pretty obvious. You put the input sequence, and then for the output sequence, you shift it 1 to the left. So if you notice, the got dropped. So the input is the dog is a. Okay. And the output is, oh no, I screwed this up. The dog is, it should have said the dog is a pet. Okay. And then the output should have been dog is a pet, end of sequence. There's one symbol you have to have in this schema that is end of sequence. You don't need any other symbols. Okay. But you do need a thing called end of sequence. When we get an end of sequence, it'll tell us we're done. Okay. Okay. It's the terminal state. Okay. Is now what you do is this. Oh, so okay, this thing here is what they call the target string. So the input and the output are both provided as training data, but there's no labeling required. So you just get the Encyclopedia Britannica. I guess nobody uses Encyclopedia Britannica. You use Wikipedia. You take every line in Wikipedia. Okay, so if you're going to have a context window of 10 tokens, then you take every sequence of 10 tokens, and then you take the sequence of 10 tokens, you shift it to the left one. Okay, so therefore, at every position, it's predicting 1 token ahead. And since it's a masked attention, it's doing that prediction with only the past, not the future or the present even. I think it's not using the present. Oh shit. I may have an error. Maybe I was supposed to have minus infinities on the diagonal. Let me go check that. Jing Song. I think I'm supposed to have minus infinities on the diagonal. Okay. 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 You good?
So the training data is coming from the left and the right here.
The training data is coming from both directions. And we're using one hot encoding here. I didn't bother putting all that in because I figured you could figure, you obviously have to tokenize it and do the one hot encoding. But you use a cross entropy loss. The cross entropy loss is the maximum likely estimate for doing, that's what you always use cross entropy loss when you want to do training for a probability distribution. Right? Everybody should know that, I think. Well, the people who have taken the deep learning course know that. Okay. So what you do, this is called generative pre-training. It's called generative because you're generating probability distributions as opposed to actual single outcomes. Okay, so you're training this thing to predict the probability distribution of each new thing. Okay? Okay, so now what you do is this. Once you've trained the thing on like 15 quadrillion billion, Harald, what is the thing that is really big? Is after zillion or peta zeta? After you train on 50 zeta bytes of data, what happens is that now you run the thing with a sequence and you only take the last token, select last token. Now that'll give you a probability distribution. You can take the map estimate, but typically they'll also do other things. I stopped reading at that point. Okay, but you can sample from that distribution with a temperature. Okay. And then this is essentially producing a Markov chain output. Okay. And it gives you the next token. And you keep running that until it hits end of sequence. Now, here's the part that really freaked me out, which I had to have a long counseling session with chat over. Okay. Which is that how does it answer questions? And the answer is you just put for the question, you just put the whole question in one go, okay? And it just knows it's a question and starts answering it.
So the question is like that, you put it on the left.
There's nothing special.
So the question, you put that on the left.
Yeah, you put the question in the left, and then it just goes, it keeps generating tokens until it gets to it gets to the end of that special token, which is end of sequence, and then it's done. Is that wild?
I have a question about
Yeah.
calculations. So is there, I feel like I would know, but is there any math that was done in all the transform layers that you can like set aside and then you come through with the new token and you're only one?
Oh yeah, there's a whole bunch of papers on how they save computation because the problem is most of the computation you're doing here is wasted, right? Now, but the argument, from what I didn't go into this because it was hard enough just to understand what the heck the thing was doing. But the reason they do this is because it's a more regular calculation rather than just compute the last output. It's not worth it. You compute everything and it all goes through and you throw away everything except for the last token. However, because of the fact that you have this masked attention layer, there's a lot of calculations that can be reused. Okay, and I didn't go into it, but you can imagine that that would be true. The correlation is that correlation matrix. When you move the sequence over one, it sort of stays the same. You just have to recompute certain values or something. I don't know. There's a lot of research that's gone into how to make this run efficiently by reusing calculations.
Yeah. I should write me a like 16,000 token sentence that's coherent. It'll get halfway through and start forgetting what it started saying at the beginning.
Well, it's auto-regressive, so yeah, it'll be like
Trying to pick it up from context of what it's.
Yeah, right. But its only state is the last 8,000 words it said to you.
Oh, that's right. In like the llama model.
At least in these basic models that people talk about. Now, the OpenAI, now it's doing this thinking thing and everything, it's probably doing something more complicated, but let's face it, that's pretty hacky. It doesn't work that great. So,
It's a pretty good code.
I think we're pretty good. I think humanity is safe for at least the next year or two. Because this model in my opinion, has plateaued. Now that I know what exactly it's doing, I'm like, oh, they're not going to get this to be artificial general intelligence. I agree with Jan. I'm on Jan's side. They need to make another step. There's gonna be some other big innovation. Okay. Yeah. Okay. Then this is how you actually run the thing. You just go, okay, this is how the input, this is what I just told you. The input is the user prompt. Okay. And then you keep repeating this until you run to until you get to an end of sequence. Okay. And each time you run the LLM with the output, with the input, and then you concatenate the output to the input. And if its length is longer than the context length, you shorten it by 1. I don't know if this is correct Python, Greg, but I used it. Okay. And and this is just some summary of some things. And oh, now this is the vision transformer. So don't worry. I'm going to go through this really fast. Once you understand this, the vision transformer is trivial. Okay, what you do is you just take the image, you break it up into pieces. Each piece, you do some kind of linear transform, okay, into a vector of dimension dm, okay? It could be, you can keep the full dimension. Xiao is an expert, a world expert on the visual transformers. So if you want to know something, you can ask him. You do positional encoding. I read on some of the papers that they do the positional encoding in 1D rather than 2 often because it's good enough. Okay. And then you put it into a transformer block. And you're good. That's it. That's the whole thing. I mean, that's the whole thing. You don't have to be scared of transformers anymore. It's just like a convolution block or any other block you use in a neural network. You just string them together. Okay. And then you can do whatever you want with it. I didn't make up these slides, so they have to be, I probably should improve them. But you can put something on the end, an MLP on the end that does classification or whatever you want to do. And yeah, I think the rest of this is we're basically done because I need to work on these slides some more. So so that's pretty much it. So hopefully that helped explain transformers a little bit in a more intuitive level. And thanks everyone. I'm going to